Hello everyone, I'm Yixin, the final year PhD student from the University of Hong Kong. Today, I'm going to present our work, Preemptive or Reduced Scheduling for Expediting Distributed DNN Training. Recently, the deep learning workloads keep increasing in the production clusters to support AI platform and AI-driven service, including the image classification, machine translation, and speech recognition. For example, Google used TensorFlow to support Google Photos and Google Speech. Facebook used PyTorch for speech recognition and online advertising. In these companies, they need to deploy and run the machine learning models in their cluster to provide their online services. However, training the machine learning models is resource-intensive and time-consuming because most machine learning models rely on GPU and they require thousands of epochs to converge. For example, it takes 10 hours to train the ResNet-50 model on a single TPU, and it takes 81 hours to train the BERT model on 16 TPUs. If we have more than 1,000 TPUs, we can finish the ResNet-50 model training in around 1 minute, and also finish the BERT model training in around 1 hour. To expedite the DNN training, one way is to train the DNN models in a distributed and parallel way. And then we need to synchronize the parameters with each other, for example, by the OR-reduced architecture. The most representative OR-reduced architecture is the ring OR-reduced. Here, we have a set of workers, and each worker processes its own data shard. And the workers need to synchronize with each other in a peer-to-peer manner. For example, after one worker finishes processing its own data shard, it sends the gradients to its neighboring worker. The neighboring worker receives the gradients, merges the gradients, and sends the updated gradients to the next worker. And then the next worker does the same thing. And in this paper, we consider the synchronous data parallel training. In the distributed training for the machine learning clusters, one fundamental challenge is that how to ensure the scalable and efficient DNN training. In the existing clusters, the scalability is usually poor because of the communication overhead. To mitigate the communication overhead, we need to consider the fine-grained communication scheduling within a single job. And we want to propose a preemptive communication scheduler to improve the performance, efficiency, and scalability of DNN training. To investigate the fine-grained communication scheduling, we need to know what happens within one single job on one worker first. Let's see an example of such DNN structure with a layer-by-layer structure. Within one training iteration, we do the backward computation first. Starting from the last layer, we compute the gradients and send the OR-reduced tensor for the synchronization. And we do the same thing for the second last layer, and then the first layer. After the backward computation is done, we start the forward computation. We start from the first layer, receive and apply the gradients, and then the second layer, and then the last layer. In this workflow example, we can find that the computation operator in the forward computation depends on both its precedent computation operator and its OR-reduced operator. So it's critical to consider how to schedule these OR-reduced tensors to reduce the waiting time of the forward computation, and then to minimize the training time of one iteration. In the OR-reduced tensor scheduling, one representative way is the weight-free backpropagation, which schedules the OR-reduced tensors in a first-in, first-out order. However, if we change the order of these OR-reduced tensors, the training time can be smaller. And if we allow the preemption during the all-reduced tensor transmission, the training time can be even smaller. Compare these three approaches, we can find that if we allow the preemptive scheduling, we can have around 25% improvement in this example. There are some recent work working on preemptive scheduling, but they only consider a much simplified problem. For example, the DNN of a layer-by-layer chain structure. However, this is not always true. The training execution model, in general, is a sophisticated directed acyclic graph. And in this graph, the nodes represent the computation or communication operators, and the edges represent the dependencies among these operators. And it's possible that we have some branch in the computation path. Another factor that is not considered in previous work is that the default sizes of gradient tensors are not often ideal because the small tensor leads to the underutilization of the bandwidth. We first investigate the all-reduced time with the tensor size. We can find that when the tensor size is smaller than the threshold, the overhead cannot be negligible. And we also show the distribution of the tensor size of two models, ResNet 50 and Transformer. We can find that the tensor size varies a lot even within the same model. So in this work, we propose a system called PACE, and our objective is to minimize the training time of one iteration. So we need to consider the following two questions: how to preemptively schedule the all-reduced tensors, and how to fuse the tensor to improve the bandwidth utilization. Upon the submission of one DNN training job, we run this job first, do the profiling to get some job information like the DAG structure, the execution time, and the tensor size. And then we do the tensor fusion to produce a fused DAG. We then feed this fused DAG to the communication scheduler and obtain the communication scheduling decisions. And then we run this job following these communication decisions. So in this work, we design a schedule to achieve the best overlap between the communication and the computation in order to minimize the training time of one iteration. In the communication scheduling problem, our objective is to minimize the completion time slot of the computation operator J. In the first constraint, we ensure that we have sufficient time slots to accomplish its all-reduced operator. And here, the variable x is the decision variable, showing that whether to execute the all-reduced operator I at time t. The second constraint is the completion time slot of the all-reduced operator I, and here, y is presented by our scheduling decisions x. The third constraint is the DAG dependency, and here, the completion time of the computation operator J depends on both its precedent computation operator and also its all-reduced operator. We also have the resource capacity constraint. We ensure that at most, one all-reduced operator is scheduled at each time slot because of the limitation of the bandwidth. And also, the all-reduced operator is scheduled only after its precedent operator is done. However, solving this problem is not trivial even if it's an offline problem. We have some non-conventional constraints for the completion time of the all-reduced operator. And for the completion time of the computation operator, it's incorporated with the DAG structure. So we need to consider how to convert it to a standard ILP with a nice structure first. Let's see the example of such DNN structure first. The training time of one iteration depends on the last computation operator 12. And the computation operator 12 depends on its precedent computation operators 9 and 11, and also its all-reduced operator 1. We can prove by induction that the completion time of the computation operator 12 depends on both the completion time slot of the reduced operator j and the longest computation path from the operator j to the end. In this way, we can remove all the auxiliary variables and keep the decision variables of x only. And then we transform this problem to a minimization problem over the lexicographical order. And we also prove that it's equivalent to minimizing the longest completion time. We then transform the lexicographical objective function to a convex function and preserve the lexicographical order at the same time. We then prove that the coefficient matrix is totally submodular, which means this problem can be efficiently solved by an LP solver. However, in the previous model, we assume that the DAG is given, but we still need to consider how to construct such DAG first by the tensor fusion. In the tensor fusion, we want to achieve a good trade-off between the efficient bandwidth utilization and the delay of execution start of the fused or reduced operators and their successor computation operators. In this example, we can fuse the tensor 2 and 3 into 2', and also the tensor 4 and 5 into 4'. However, for the fused or reduced tensor 2', it can only start after its precedent operator 3 is done, and its successor computation operator 8 can only start after the whole fused tensor has arrived. So for the design rationale, we fuse the or reduced operators with a similar ready time. This can be done by sorting these or reduced operators according to their ready time. We also ensure that the sizes of the fused tensors are similar and sufficiently large. This is to lower bound the worst performance of the communication. And we achieve this by maximizing the minimum total tensor size among the partition groups. So in the previous example, we can sort the 6 or reduced tensors in such an order and fuse the middle 4 tensors into 2 groups. In the evaluation, we do our experiments with MXNet or reduce, which is based on the Harwood communication library. We compare the performance of our approach with different benchmark models, including VGG16 and Transformer. In VGG16, it has 32 or reduced operators and 80 computation operators. And in Transformer, it has more than 100 or reduced operators and more than 1,000 computation operators. The number of parameters is around 100 million in both of these two models. We compare the performance of our approach with 3 baselines. The first baseline is weight-free backward propagation, which schedules ready or reduced operators using first in, first out without any kind of tensor fusion. The second baseline is default Harwood, which is weight-free backpropagation with the fusion of small tensors. The third one is tic-tac, which reduces the blocking time of forward computation by changing the communication order of all reduced tensors. We first show the training speed on the different number of workers. Here we set the bandwidth as 10G. We can find that our approach achieves up to 32% improvement in the training speed. Especially when the number of workers is larger, there is a much larger room for us to improvement. Next, we show the training speed on the different bandwidth. We find that our approach achieves higher training speed on the same bandwidth compared with all other 3 baselines. We notice that the room for improvement in training speed depends on both the computation speed and the bandwidth we have, because the maximum overlap between communication and computation is equivalent to the backward and forward computation time. So when the bandwidth is too small, the communication time is too long compared to the computation time. So there is not much percentage for us to make improvement. But when the bandwidth is large enough, the communication is no longer a bottleneck. So there is not much room for us to improve either. For example, the communication can be finished before the backward computation is done. So the performance of different approaches is quite similar in this case. However, in the production cluster, the computation power of GPU they have is much larger than what we use in our experiment. So we can still make a lot of improvement at a higher bandwidth in the production cluster. Last, we show the bandwidth usage in the training process by showing how much bandwidth is used at different times. We can find that our approach reduces idle time in the network usage, which means our approach has higher bandwidth utilization than the default hardware would. To summarize, in this work, we propose PACE, a communication scheduler for distributed DNN training acceleration. We identify that there is a big potential on improving the resource efficiency in ML clusters. For the future work, we can consider the device placement. For example, try to reduce the transmission cost of intermediate data. We can also consider the GPU sharing to improve the GPU utilization. For example, we can consider to collocate multiple jobs on the same GPU card. That's all. Any questions?